Okay, good evening, everyone. So, this is welcome to the third live session for the Aqueous Corrosion and Control course. Today, I'm going to start with the second assignment first. Discussion with the assignment. So, I'll go over one by one all the questions. So, the first question: determine the current potential and corrosion rate for zinc in one normal scale. Um, Assuming that the zinc surface acts as the cathode and cathode, and Tefl slope is given as 0.1 volt, and exchange current density for the zinc and hydrogen are given as 1 and 414. We are given the standard reduction potential for zinc and the zinc concentration. So first we need to calculate the the equilibrium reduction potential for zinc. Here the reaction zinc plus 2 electron becomes zinc, and equilibrium standard reduction potential was given, and then 2 zinc minus 0.76 volt. So E and then 2 plus I can substitute minus 0.76 plus 0.0591 get that 2 hold on, minus sign into the concentration on top. So finally plus this sign. Concentration of zinc ions is 10 to the power 6 minus 6. We get 0.76 plus 0. I'll take out the minus 6 out. Minus 6 divided by 2 P into 0.0591, which is 0.9373. So this is the reduction potential, the equilibrium potential. Now we use the Tefl relation. Eta anodic is equals to Tefl slope beta anodic log of I naught given. So um, just to explain what is happening. Uh, log of I E. This is your big reduction potential, and the 0.76, and this is your hydrogen. This is H gives H plus plus electron. This is your H plus plus electron. Anodic reaction or a cathodic reaction. H and anodic zinc reaction would be zinc zinc is zinc plus 2 plus 2 electron. And the cathodic reaction, zinc plus 2 plus 2 electron. Zinc. Okay. The intersection point is your E core. Mm, this is your I core. We're given this, so we just have to find out the intersection point here. So if you know the starting point, so this is the exchange current density for zinc is given as 10 to the power minus 1, and for iron, oh sorry, hydrogen it's given as um, should be on the other side, but the way I've drawn it is 10 to the power minus 4. This should be over somewhere over here actually. So, you have two equations. You have these two lines. You know the slopes. Careful slope you are assuming is 0.1. Here is also 0.1. All of them are 0.1. So you have line with slope 0.1, and the start we have 1 point. If you just write the equation of the two lines and find the intersection point, we'll get the answer. Uh, which is also another way to visually think of the problem. The TEFL equation also gives you the same thing. So eta A, where E core minus E is in, E is in 2 plus E is equals to 0.1 log of I core divided by I naught. This you have to calculate minus of minus 0.9373 is 0.1 log of I core divided by 10 to the power 0.1. And the other equation is hydrogen uh, reduction. E H plus H2 plus S2 0.0591 to log of Hn concentration square divided by Ph square. This here given as 1. Since the concentration is 1 normal, so this is 1, and this here is assuming 1. Yeah, only one. So this entire thing becomes 1, 0. So your second equation of the second line becomes E core minus 0 is equals to minus 0.1 log of I core by 10 to the power minus 4. Now you have two variables and two equations. You just need to solve them. So I just equate the E core values. So 0. 0 is equals to minus 0.9373 plus 0.1 log I core divided by 1 10 to the power minus 1. mm, is equals to, so this term is, I'll just send this to the other side. So this is equals to -1 log of I power 10 to the power -4. Taking this to this side and side, and we get 0.1 common log of I power 10 to the power -1 into I power 10 to the power -4 equals to 0.9373. And we get I core is equals to 9.373. Yeah. And this becomes 10 to the power -5. So add, add 5 this time. That's just it. Log of I power square minus plus log of 10 to the power 5. Okay. So 9.373 and I core square is equals to 10 to the power 4. 373. Yeah, I got it. So I'll get the value of 153.63 amps per centimeter square. And if you just substitute the value of this I core in this equation, and you or in this equation, you'll get the value of E core. And incorrect answer was C. So, so V core comes out as minus 0.618, and I core is this. I got some emails about few questions. I think fifth one, there's a mistake. Diffusion length should be 100, and also they haven't missed an exponent. Yeah, I'll go. And second question, if an iron rod of area 1 centimeter diameter and 2 centimeter length is immersed in sulfuric acid pH2, show E core of minus 480 millivolt versus this is given against a standard caliber electrode. What would be the hydrogen or voltage for cathodic current density of 8 milliamp per centimeter squared given cathodic cathode slope is this 8 volt per decade 0.8 and corrosion current rate the current is given as 500 microamp. We are given the ferrous ion concentration. The standard R reduction potential is plus This should be centimeter square. So since the value of I core was given in terms of centimeters. Okay, yeah, I get your point. So the current densities are given in meter square, so this has to be meter square. So hmm, this is meter square, amps per meter square. So the correct answer would be, if you convert it in centimeter square, 153.63 square amps per centimeter square. And none of the option match.
I think there is some problem in the unit in the options.
Yeah, I think, yeah, and none of the options match if you take the correct units. So yeah, it should be 153.86 amps per meter square. Okay, thanks for pointing it out. Okay, so again, now we're given the two reactions versus your selection of iron and your hydrogen reduction. Yes, so we are given the value of P core, which is minus 0.48. This is versus SCE. So to convert it to SHE, you need to subtract the point 0.823. Two four one four. You need to add, so to convert it, equal to minus 48 SCE equals to minus 0.48 plus 0.2414 versus SHE. Now this becomes 4.8 minus 2 point minus 0.2386. And given that value of corrosion current. Yeah, corrosion current is given. It's 500 into 10 to the power minus 6 amps. So we need to divide it by the area to get the current density. So area would be pi r square uh, sorry, 2 pi r. So we just considering the curved surface area. We're ignoring the hot top and the bottom. I mean, it's not mentioned in the. Okay, so yeah, we're ignoring the top and the bottom face. We're just assuming the curved surface area. Curved surface area is 2 pi r h. So that becomes 2 into 5 into r is half. To h is 2. So 2 pi divided by 2 pi. This is your current density. Because we are given this value 0.760. This is minus 0.44. Turtle slope here given for cathodic turtle slope. So the cathodic turtle slope is 0.08. This is the direction H plus electron, H plus electron gives you H. Fe goes to Fe plus 2 plus 2 electron, and Fe plus 2 electron becomes Fe. What else are we doing? That is at concentration. We're also given the cathodic current density. This is 8 milliamp per centimeter square. Yeah. I think that's all. The pH is given. That's the sign concentration.
8 milliamp per ampere is the cathodic current density or exchange current density. It has been marked at exchange current density.
Oh, cathodic current density 8 milliamp. Hmm. Okay, we are applying external potential, right? The iron load is a solution. Also, not the exchange current density. Cathodic current density will be different. Okay, and let's see. Sign concentration is 10 to the power minus 2. And okay. And these 2 points shouldn't be. Um, let's calculate. We're given the numerical list percent, and I'll go back to the figure. So we're given 2H plus 2 electron times H2. So EH2 is 0.059 divided by 2 log of X plus ion concentration, pressure, partial pressure of S2. Again, it's not given, but we are assuming it is 1. 0.059 divided by 2 log of 10 to the power minus 2 square. 0.059 into minus 4 by 2 minus 2 is minus 0.1183. At that point becomes the reduction potential hydrogen is minus 11, minus 1.82. Now we can write our TEFL equations of the cathodic. We have minus beta C log I over I naught. And the cathodic TEFL slope we are given minus 0.08 log of I from I naught. So this is your econ minus of minus 0.1182 and 0.08 log of icom or I corrosion. It's the same thing. I corrosion we calculated 500 into 10 to the power minus 6 into 2 pi 256.28 not. So ecor we are given this value and 0.2386. So minus of 0.2386 plus 0.1182 is equal to minus 0.08 log of 6 into 10 to the power minus 6 and not. If you solve this, you get I naught is equals to 2.48. Hope this number is correct. Okay, so this is your I naught. So this standard reduction potential for hydrogen is 0.11 sorry, plus minus 0.1182. This we just calculated. This were given and this were given. And this will be different. Um, Now we are asked what would be the hydrogen over potential? Okay, if the cathodic current was this. Okay, so now we have the value of the exchange current density, which is this value, and now we use calculate the over potential required to get the cathodic current of this value, this 8 milliamp per centimeter square. So we are given eta C is to 0.08 log of 8 into 10 to the power minus 3 divided by 2.488 into 10 to the power minus 6. So you'll get the value of 3 4 into 10 to the power 3. So yeah, this is very high voltage.
Can
Uh,
you please check this calculation, this last step over voltage? Will it
oh,
come 3.214 into 10 is 3?
okay. Let's check 0.08 log of 8 divided by 2.48 into 10 to the power minus plus 3. Um, mm, 8 plus log of 10 to the power 3 is 3. Um, divided by 2.488. This minus sign would be something now, right? Uh, or it would be the negative value. Yes, is 0.08 into this is 3.215. Is this the value you were getting? Plus 3 into 0.08. That's around half a volt minus 0.497.
Log 8 upon 2.48, log base 10, it will be 0.508.
Okay. Mm, maybe I made some mistake. Okay. Oh yeah, I didn't take the log. Yeah. 0.507 plus 3 uh, minus 0.08, and that becomes 3.5. 3 into 0.08. minus 0.38 volts. Like, this guy, yeah, in the solution, he forgot the log and even removed this part. I don't know.
Actually, 3.214 into 10 raised to the power 3 volt is actually very high over voltage, which I don't think it's feasible in. Uh, it's 3.2 kilovolt. Is
Yeah,
it feasible in CT such high over voltages
I
in
don't know.
corrosion cathodic?
Yeah, I don't know. That seems different. Yeah, the actual answer would be this anyways.
Minus 0.28 volt is okay. That can be
Yeah,
achieved. But
yeah,
3.2
yeah,
into 10 raised to the power 3 volt, that is 3.2 kilovolt.
yeah, yeah. I'll inform the NPTEL team that the answer is incorrect. In the first question, I'll let them know that they are incorrect. And I think in the fifth question, also there's a mistake.
So what answer will be considered for this question? Actually, I have marked that 0.321 321 volt. So what will be the correct what answer will be considered as correct for this question?
I think they should give a bonus. I'll ask what will they do. Like they should give marks to everyone else. In the last course I took, there was this was an issue, so even I am not aware how they will resolve it. But yeah, most likely they should do this, or they'll remove the question itself maybe. In the performance, determine the potential applied, which causes tenfold decrease in the corrosion rate of iron. So okay. So we got our values. So it should be the minus 0 point minus of 0.44. So this value would become something like minus 7 point something. Seven two. This is minus 7.0.72. Hydrogen. So we asked what should be light potential for tenfold decrease in the corrosion rate of iron. We have to. This was the E core. We asked what should be like. We externally apply some potential to shift it to this point. Yeah. So given Fe plus 2 plus 2 electrons, Fe 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 is minus 0.4 plus 0.059 divided by 2 log of 10 to the power minus 6 atom concentration with minus 0.44 and minus 3 into 0.059 that minus 0.59 minus 0.617. That's it. So writing the Tafel equation, core is log of I core divided by I naught. This was our first equation. According to the initial condition, now we are asked what is the E applied. E Fe 2 Fe beta log of divided by. So this I core needs to be reduced by 10. So I core by 10 into I naught. So now just subtract these two equations. If we subtract 2 from 1, we'll get E applied minus E core. That equals to beta is common and I core 10 into I naught into to subtract it will be inverse. So I naught divided by I core. These three terms cancel out. There's a log beta a log of 1 over 10. Okay, I'm going to write. So E applied minus E to beta a log of 10 to the power 1, so minus beta A. Which 0.08. So here they've taken still on the right. So we calculated the E-core from here. E-core equals to minus 0.28 minus 0.44 minus 0.2. So we applied so minus 0.72, that's minus 0.08. We applied, it'll be 0.72, 0.08. Is it correct? 0.8. Again, there's no option. And I'm solving this question for the first time. Okay, the second question. Did anyone got the correct answer in third question as well? I'm getting 0.8. I guess maybe since the last question, the answer for the last question was incorrect.
No, I got minus 0.3186 option D, which is correct in this case.
Really? Do you know what mistake I'm making?
My net was disconnected. I haven't followed you.
Okay. This is E1 versus SC. Okay, I'll check this answer once and I'll go to the next question. And did solve this question before. So I know this is correct. Okay, a zinc piece of area 5 centimeter cross 5 centimeter cross 1. Lime should be immersed in 1 molar HCl for 1 day. The potential of 0.6 minus 0.6 is applied to the zinc by an external mean. Calculate the rate of zinc in the solution and the amount of current that needs to be applied externally. Assume that the entire zinc surface acts as the anode and the cathode. We're given the zinc standard reduction potential. The current density for the zinc reduction and for the hydrogen reduction. We're given TEFL slope as 0.1 volt Okay. So again, I find it helpful to make notes. Okay. So we're given this time. This here and this is here. So this here given as 10 to the power minus 8, and this is 10 to the power minus 6. This for the hydrogen, and this for zinc. We're also given this standard reduction potential at 76. We're given a head sign concentration, and yeah, so we asked what if some potential is applied externally, what will happen? So one thing in this question, we are ignoring the hydrogen production, the current taken up by hydrogen production. So we are assuming all the current, uh, all the electron produced by the solution of zinc are uh, goes in the external circuit, and none of it is taken by the hydrogen. So if you calculate it, the amount comes out really small. So it's kind of, we can ignore it. So for zinc plus 2 electron, zinc we can write 0.76 plus 0.059 divided by 2 10 to the power minus 6, and 6 into 0.059, and we'll get minus 0.937. Next we'll write the Nordic Staffel relation. Eta Nordic equals to A log of I E applied minus P equals to 0.1 log of I applied divided by your exchange current density for Nordic action 10 to the power minus 8. You get minus E applied external is 0.6 minus 0.937 to 0.1 log of I applied divided by 10 to the power minus 8. 0.337 divided by 0.1 is equals to log of I applied plus 8. log of I applied is equals to 3.37 minus 8 minus 5.63. So I applied, so 10 to the power minus 5.63, which we should get 2.34 to 10 to the power minus 5. This is amps per centimeter square. This is the current density. Now you need to calculate the current. So you're given your piece of metal, 5 centimeter cross 1. Its surface area is for these two faces is 5 times 5 into 2 for two faces 50, and for these four faces it's 5 cross 1, 5 cross 1 into four faces, so it's 4, so it's 20. The total surface area is 70 centimeter square. So just multiply it with the total surface area and we get the answer. So I current reaction source is 2.34 into 10 to the power minus 5 into 70, which is 1.64 into 10 to the power minus 3. So 1.64 into 10 to the power minus 3. And now to calculate the corrosion rate. Corrosion rate. So we're given the current 1.64 into 10 to the power 3 divided by the electron, the Faraday number 500 into number of the charge transfer number. This will you'll get the total number of atoms getting reduced, oxidized per second. You need to multiply it with the density. It will 0.38, and this is per second, so into 365 into 3600 for seconds in hour, 24 hours and 365 days. And I need to divide it by area. Since, the corrosion is happening at every surface, so we require like how much thickness is getting eroded per year. That's the mil MPY. Mil is again a unit in uh, what do you call it? In inches, 10 to the power minus 3 inches in mil. So if you do this and 1 point, As always, you'll get 0.35 then. That's so this is centimeter per year. Now, if you want to convert it to inches, divide by 2.54, and to convert it into MPY in 10 to the power minus 3, the answer is 13.82. Okay. Okay. Now this. Given the data for O2 diffusion, so they were given diffusion coefficient at 200 degrees Celsius. Solubility of water is given 4 parts per million. Taking their thickness is 100. Potable intensity. First, we need to find the concentration of oxygen. So, okay, our cathodic reaction is O2 plus 0, 4 electrons. Yes. 4 OH minus. So we're given concentration of 4 ppm. Convert this. So what I found was whatever value you get in ppm, in by 1000 into 32. This is your to concentration. So what I got is 4 into 10 to the power minus 3 divided by 32. So 0.125 into 10 to the power minus 3 moles per liter. Yeah. Since the diffusion coefficient is in centimeters, so it would be better to write it in terms of moles per centimeter cube. That's moles per liter, so liter is 1000 centimeters square, 100 centimeters square. Oh, no, 1000 centimeters square. Moles per centimeter square. 0.125 into 10 to the power minus 6 per centimeter square. So the formula for limiting current IL
Should be centimeter cube in place of centimeter square.
Oh yeah, centimeter cube, yes. So I just remember 10 cross 10 cross 10 centimeter is 1 liter. 10 to the power 3 centimeter cube is 1 liter. So diffusion coefficient into your bulk concentration, Cb into N F divided by your diffusion layer thickness. You get 0.3 into 10 to the power minus 5 into 0.125 into 10 to the power minus 6 to 4 times 96500 divided by 100 into 10 to the power minus 6. Like this. It will give you 14.475 into 10 to the power minus 9 times per centimeter square. Oh, no, minus 6, sorry. Minus 6.
So the answer of this question is 14.475 10 to the minus 6 ampere per centimeter square. But in the solution provided on the portal, it has been given as 20, just twice of it. The calculation of diffusion layer, the value of diffusion layer thickness has been taken as 50 in the solution, which has been updated.
Yeah, I think it says D is correct. So let me take the entire picture.
This is correct. What you have done is correct, but the solution which has been uploaded on the portal,
Even solution is
in that the
correct, and this says D is correct, but D is obviously not correct. Even it is incorrect.
the C will be correct or D is correct. I think C is correct.
C is correct, yeah. So
Okay.
I mean, I didn't submit, but it says accepted answer is D, so that's incorrect.
So I opted for option C. Then my answer has been marked as wrong.
Yeah, okay. I'll ask them to correct. Like I'll submit all the correct answers to them, and yeah, hopefully they'll update it soon. Okay. Let me change last question. Change in the corrosion potential is 0.2 at given pH, then the corrosion rate of metal increases by how many times? We're given the corrosion, the anodic tackle source. We have our corrosion metal goes to metal plus 2 electron. We're given eta K is equals to IE I naught. Okay, we have our two equations. So now store 1 minus metal plus 2 to metal equals to beta K log of I power 1 divided by I naught. The second equation is I for 2 minus 2 n plus 2 and log of I 2 not. Just subtract these values, so e power 2 minus e power 1. Okay. Beta A log of I power 2 divided by I naught into I naught divided by power 1. A log of power 2 divided by I power 1. This potential is given as 0.2, 0.06 log of power 2 I power 1. We take to the other side, it's 100 over 3 or 10 over 3 log of I power 2 divided by I power 1. Let's take the log, so I power 2 I power 1 equals to 10 to the power 3.3. I think this one is correct. We got the answer 2154.4. Okay, so I'll ask the NPTEL team to correct the answers. Okay. Let's see this week's assignment. Yep. So I think tomorrow is the deadline for tomorrow's assignment. I can go over like the thing. And the second question is thank you. Done questions like this before, like in this assignment itself. This should be doable. Corrosion potential and corrosion rate for zinc in 1 molar HCl. Assume all zinc surface across. Tactile slope is given. Change current density for zinc and hydrogen are given. Yeah. The second one we can do. Something is to evaluate the corrosion rate. So here there was a slide where they professor discussed like, there are two techniques to determine the corrosion, like the corrosion rate. First is the TEFL method, and second was the linear polarization. So one of them is destructive, and the other one is not. So you just need to look at the slide, and I can give you the exact answer. So whichever is the destructive method, you don't want to use that one. Hmm. Four by X diagram, I think we didn't cover it in these three lectures. You need to, you can Google it, what it is. Simple. Then you're asked about the passivation, I think. So, so for passivation, you had few terms. What are terms? So during passivation, what happens? It's log I, yeah, E. This is the current passive current density, E. This is the critical current density, IC. This is the EP, passive potential, and this is the trans passive dissolution. Trans passive or repeating. Okay. So what happens if you increase the corrosion rate up to a point it increases, and after that it starts forming oxide layer or a passive layer on the surface. My screen is not visible. It's visible. Maybe that might be a internet issue. So the current density increases up to the point when you uh, change the metal ion concentration or something like that in the solution, or increase the amount of acid in the solution. So up to a point, your corrosion rate increases, and after reaching this critical current density, it suddenly drops to this value, uh, which is a passive current density. It's not zero, but slowly, but corrosion is reduced a lot. And if you increase it further, the current density doesn't increase. Uh, but after a point, your tipping will again start corrosion, the dissolution of metal produces the transpassive dissolution area. Special definition. So in the question they have given you different metal alloys which have different uh, critical current density, different uh, passivation current density, and your EPP, passivation potential. Yeah. So you need to apply the mixed potential theory and set the corrosion rate of the alloys. Mm-hmm. Different velocities. Okay. I think we just need to make these plots. So under stagnant condition, we will make plots for different metals. So would be like something. First would be like this. It would be like this. And just see where the values are, and depending on that, under stagnant condition, we will have some rate limiting redox reaction happening. Sorry, the reduction reaction happening. And with oxidation reduction, maybe. So wherever the intersection point is, you can like see you can reach the road fast. I think three questions are solely based on this. There are different cases, like there are different velocities for the flow. Addition of oxidizer, what happens to the system? This again was covered in the lecture, so very short, like what happens if you add Fe plus V. You have your iron, you have your hydrogen, and you add this is your hydrogen, electron, Fe plus 3, this is Fe plus 3 plus electron, Fe plus 2. So this is your oxidizing species, right, which takes up the electron. This is your Fe plus 2 electron. So what happens here? Uh, so this is the reaction, plus electron. So there are now two oxidizing species, right? So this is Fe is getting oxidized, and these are getting reduced. So two species are getting reduced. So these two are competing with each other to get the electrons. What happens is after reaching this point, and this is your point where the mixed potential is applied. So depending on that, you can see like whether the corrosion rate is increasing or decreasing, what's happening to the hydrogen evolution. Earlier, uh, this was the point. So this current was amount of hydrogen it was getting released. So now it will be something somewhere over here. It's decreasing. Yeah. And the corrosion rate of the iron is increasing. Uh, Before it was somewhere over here, and now it's increased to this value. So the corrosion rate is increasing. Okay. I think next assignment is relatively easier. Okay. If you guys have any doubts, you can ask me in any of these questions. Otherwise, you can end the session here. Okay. Okay. I'll ask the NPTEL team to correct the solutions, and we will give them the solution again, solve it on time paper, and so they can upload. Maybe if they want to, they can upload the right solutions or others. Okay. Okay then. Thank you for attending. Bye bye.